And we sort of came up with a nice example of why this kind of logic is powerful, right? The first thing we observed was that the even just with the logic for the monoids, we could say things about decomposition that is much harder to say in ordinary classical logic, or even intuitionistic logic, right? We were able to talk about primality, and then we related that primality theorem to an application in concurrency, where primality picks out exactly the single-threaded processes. So that, to me, that's a foreshadowing of where we're trying to get to. Okay, so what we haven't talked about, and what needs to be a little bit of preface, is the modal logics. So the people have a little bit of background and understand where this comes from. It goes all the way back to, so there were the modal logics have quite a long history. I studied them in high school and then in college. There's here, let me show you. So I studied out of Chellis and out of Cresswell and Hughes. And the way I structured my studies with Rich Salter at Oberlin College was I would lecture him. So I went through and picked out what I considered to be the most important theorems. And even though they were presented as formal systems before it was discovered, there was a semantics that was developed by this guy. And all these things lying around. Saul Kripke. And Kripke developed the possible world semantics. So essentially, you have these operators, diamond and for possibility, and square. I don't know if I can do that, for necessity. And the idea was that at each world you had different propositions that were true, and there was a set of relationships or traversal relationships, or there are a set of relationships amongst the possible worlds. So those worlds are reachable. The relationships are called reachability relationships, and possibility says that you can reach a world from the world that you're in, where the proposition that you're looking at is true. So diamond phi says that it's possible from the world that you're in to reach a world where phi holds, and box phi, or necessarily phi, means that from any world reachable from where you are, phi holds. So those are the two possibilities. So there exists a world reachable from where you are, where phi holds, and for all worlds reachable from where you are, phi holds. Hopefully that makes a little bit of intuitive sense. Does that land? Are people understanding the basic idea? I mean, I can turn on screen share and we can write this down for folks.
Reachable is sort of a nebulous concept for me.
Okay, it will get a lot more crisp in just a minute. But let me, okay, so that shouldn't say by simulation, it should say.
Is this can be understood in terms of client server?
It can be understood in terms of programs. Client server is one kind of program.
Okay.
Okay, so the basic idea is, let me get rid of this and turn on screen share. There we go. Okay, so if you remember last time, we started to look at some logical formulae. And if you can see here, I've kind of hidden the grammar for the formulae inside the semantics, right? So really the grammar is phi, comma, c is of the form true, not phi, phi and c. And then these things here, curly e, curly or italic e, italic gi, and phi start c. And this stuff comes from the fact that our collection was a set, and this comes from our term formation stuff. That was the basic idea. And so in the world of modal logics, we introduced this idea of let's see if I can go find, well, normally I write it like this because it's ASCII, but let me go see if I can find a diamond here. All right, did I happen to have it? No, it looks like I don't have it there. So let's go. It might be under bullets. Yeah, there we go. So there's the box. So let's add that to favorites. And then see if we can find the diamond. Does anybody see the diamond?
There's a smaller one at the row underneath, all the way on the left-hand side.
This one, yeah, you're right. It's a small one. What's it called? Ah, here we are. Let me see if I can grab a bigger one. Okay, here we go. Favorites. Still tiny. Okay, that's good. Let's see. And then go back to bullets. And then go here. Looks like to favorites. Ah, oh, close enough. Anyway, so we have diamond phi, which means possibly phi, and we also have another one, which is necessarily phi. That's written this way. Okay. All right. So that's weird. Let's see if I can get them to be the same size. All right, close enough. It doesn't matter so much right now. All right. So and now what we need to do is we need to talk about the idea of worlds and reachability. In Kripke semantics, he just hypothesized that we had a set of worlds, and that there was a relation, a reachability relation, right? So I'm here, and I can reach to this other world over there. So that's and he didn't really, and nothing more was said. It was just that's the universe that we take. But we have a natural interpretation in terms of rewrite systems, don't we? So what would be the natural interpretation?
The worlds that we can reach being our possible reductions.
That's right. That's exactly right. So the A world is a program state. And when we're talking about rewrite systems like lambda calculus or pi calculus or the row calculus, there's nothing else in so program terms are our state, right? That's it. There's nothing else. The terms carry all the information you need in order to do your rewrites. Okay, so we have a world that carries that is our program state, and that carries everything. And then the reachability relation is the rewrite relation. So so notice that we've kind of set ourselves up rather nicely, right? In the sense that the term structure picks out the structure of the world, and then the rewrites pick out what we can do with this structure in terms of where we're going next. It's literally a rewrite is our this how we rewrite is determined by the structure of our term. And the row calculus is a really good example. So Matthew Hennessy and Robin Milner noticed this for process calculi. It had been noticed before that that modal logics with the Kripke semantics sort of fit very, very nicely. Now here I should make another connection for you so that people understand kind of that there are two ways to think about proving things logically, and they can and should be correlated. One has to do with proof theory, and the other has to do with model theory. So far, the way I've been introducing this logic is all in terms of model theory. So rather than talking about how from a given formula I can get to a new formula, you know, just in terms of the shape of formulae, I have been talking about how I can give the semantics of a formula in terms of the recursive structure of formulas. So the two are related, and they can and should be related, but they're a little different. So in particular, the jump from, you know, the original presentations of the modal logics to the Kripke semantics is moving from proof theory, where we just talk about some inference systems, right? You can think of it as a kind of rewrite systems for logical formulae, some inference systems, over to semantics of formulae, where we give an interpretation of the formula, and those two things are related, but they're different. So the Hennessy-Milner approach is all about the model theory, and model theory leads to what's called model checking. So one example of like in the case that we have in front of us right here, if we want to check to see that a formula is true or semantically meaningful, then we just check to see that its inhabitation, right, the set that is the meaning of the formula, is non-empty. That's the result. That's the way this particular semantics works. So absurdity, a formula that has no, it becomes a formula that has no witness. There's no program, no term that bears witness to that formula, that inhabits the formula. In the case of when we think of formulae as types, then I think everyone is familiar with the phrase type inhabitation, right? So the inhabitants of a type are those programs that type check against that type. It's the same idea, right? The inhabitants of a formula are just those terms that show up in the semantics of the formula as given here. And proof theory runs the other way. So you have some term formation rules for formulae themselves, so formulae as terms. And then you have some inference rules, which you can think of as rewrite rules on that term system for how to derive new formulae. And the two need to be related. Now, in the Hennessy-Milner interpretation of the modal logics, it's entirely model checking. There's no real proof theory there. So, I mean, if you go look, just so that people understand precisely syntactically what I'm talking about here, let me just bring out, let's see. Okay. I think that's it. Looks like I don't have it locally. Yeah, I don't have it locally. Let me just grab a browser. All right, so I assume everyone has this one. Okay. All right, so we'll zoom down. Here we go, logical characterization. So here's the logic that Milner presents in the polyadic pi calculus tutorial, right? So he has agents on the left, and which are effectively like the full range of processes. And then he has logical formulae on the right. So, and this is the satisfaction relation. So the satisfaction relation is a little bit more abstract. And what I did, and in this presentation here, you get that a formula, a process satisfies a formula if and only if it lives in the meaning of the formula. So that's a definitional thing. Okay, so let me just write that down for people. So we get some term M. Oops. Some term M satisfies, and let's see if I have the double turnstile picked out. Yes, I do, yay. Satisfies a formula phi, and then if and only if. Phi, if and only if phi lives in the meaning, P lives in the meaning of phi. Fix that. oops, M lives in the meaning of okay, so that's the basic idea. So looks like I missed a fee here. Okay. All right. So that's the relationship of this semantics to this semantics. Here he's been more abstract about satisfaction. And satisfaction could be the type judgment, right? It could be the colon. So A colon T. Now here the way to read his semantics is very similar to the way to read our semantics. A process is not constrained at all by the formula true. So if you go over here, you'll see that that's exactly what's going on. True is the entire language of terms. So if we go check out this satisfaction definition, we'd say M satisfies true if and only if M is in the meaning of true. Well, the meaning of true is all the terms. So that means there's no term that doesn't satisfy true, which is exactly the same as this here. Similarly, we say A satisfies phi and C if and only if A satisfies phi and A satisfies C. Well, let's look at what that would mean here, right? So that's this one. So M satisfies phi and C if and only if M is in the intersection of the meaning of phi and the meaning of C, which means that M is in phi and M is in C, which means that M satisfies phi and M satisfies C. People follow that?
Yep.
Sweet. Yep. Okay. So all of these end up being the same, but now here are the interesting ones. So this is the modality one. It says that A satisfies possibly alpha C if there's some alpha A prime such that A commits to alpha dot A prime and A prime satisfies phi. So if you remember the commitment relation effectively means that this thing is a sum of it's a sum of or a par of agents, and that one of them is alpha dot A prime. So effectively what this means is that it is possible for A to do alpha and then become A prime. That's the rewrite. So this is exactly what we want. Now you can look at these other cases, but it's quite interesting. Notice how the structure of the term correlates to its rewrite, and then we use that structure and pull it back into the structure of the formula. Okay, so that's one piece of the puzzle. So what we've talked about so far is we've talked about the idea that first of all, we distinguished model theory from proof theory. We've established that the Hennessy-Milner formulae, and here's an example of one such, are model theoretic, which means you use model checkers. And we distinguish that from proof theoretic, and the sort of the tools that one uses, I forgot to mention that, are theorem provers. Right, so theorem provers go and explore theorems. They explore the rewrite side of formulae via the inference rules. And model checkers go and explore the semantics side of formulae via either the satisfaction relation or the interpretation that we've given. Okay, so that's what we've covered. And then we also observe that the Hennessy-Milner logics are related directly to the Kripke semantics of possible worlds, where the states are the worlds and the transitions between the states are the rewrites. And then now for the first time we've started to see how we can get these operators out of the shape of the terms and the rewrite system. The one thing I didn't mention is that typically you have a kind of Demorgan relationship between necessity and possibility. Does everyone know what the Demorgan laws are for just normal logic? Okay, so the Demorgan laws are pretty straightforward. Notice that I didn't talk, so in this logic, I only talked about not, true, not, and on this part of the logic. I didn't talk about or, but or is a natural conjunction. It's a natural binary operator that we typically want to be able to have in our logic. And the reason I don't talk about or is because we have a relationship of the following form. If I say, not phi and not phi, and I negate that, then that is the same as let's take this out. And in fact, we define it to be. And instead of doing that, we use disjunction. What's our favorite disjunction? Let me just go grab one off of the math symbols. There we go. There. So there's conjunction and there's disjunction, right? And we simply we take this as definitional. Rather, in sort of introductory logic courses, you would be asked to prove that this is the case. You'd be given an or, a definition for or, and a definition for and then you would be and a definition for not, and you'd be asked to prove that these two are equivalent. But you can take this literally as the definition of disjunction. This is, you can define or in terms of not and we know this also from things like building logical gates, right? So and, not, and true are a basis for ordinary Boolean logic. False, not, and or is also a basis for ordinary Boolean logic. So rules of this form were discovered originally by Demorgan, and so they're called the Demorgan rules. So necessity and possibility also follow the Demorgan rules. So in general, so let me just reorder these a little bit. So typically, if you look here, he doesn't give necessity. He only gives possibility. And that's because he has, likewise, he only gives true and not. So he picks that particular basis. Here, he only gives possibility, not necessity. And the reason is because he defines necessity in terms of possibility. So can anyone guess what necessity is going to be defined as? Just following.
Not possibly not phi.
That's exactly right. That's exactly right. That's the idea. So that's the. So then you can kind of get rid of necessity this way, and define it this way. And that's what's going on here. So he has because he's got the not and the possibly, he's set up for necessity. So this ends up being a basis for his logic. And we do the same thing in namespace logic as well. So that's that sort of picks out that little piece of the puzzle. And now the next piece of the puzzle is what do we use to so notice here the diamond and the box don't have anything between the braces. All right, so here Milner has an alpha between the brackets, right? If you remove the alpha, you just get an empty, a diamond that with an empty element in it. So what the question is, what's the relationship between the empty one and the one with alpha? And traditionally, the way that's done is that you say for all alpha. So the diamond is, so possibly phi means that for all the alpha, which gets you from where you are to A prime, they all satisfy phi, right? And then you extend that via the Demorgan that way. Or you can also quantify it out via there exists. Those are two different ways to quantify away the alpha and empty out the diamond. Did everyone understand what I just said there?
So the diamond is existential or universal?
So you can give consistent interpretations either way. Essentially, what you're trying to do is get rid of the alpha. So the way you get rid of the alpha is you bind it up in a quantifier. So for all or there exists, either one. The diamond is an existential in the sense that there's at least one path out of where you are. So here, notice that there's an existential quantifier right here, right? It says there's at least some, you can find some A prime, and that A commits to, and then and A prime satisfies phi. Right, so that's the basic idea, and then to get rid of the alpha, you quantify again over the alpha, right? So you can either do for all or there exists, and both of them give you, slightly different flavors of logic. But it's just a trick of using quantifiers to get rid of, to bind away variables like this. So that's the relationship between the empty diamond and the diamond that has something in between the two brackets. And now comes the next thing. What can alphas be? So in the case of the polyadic pi calculus tutorial, alphas are barbs, right? So here it's either an X or a Y. So this corresponds exactly with the barb. It's not the full prefix, right? It's the location, right? It's saying essentially that there is some commitment inside A that's located at alpha. So there's either abstraction or a concretion located at some alpha, whether it's X or Y or Z or what have you. Yeah, so that's what's being said there. But that then leads to this tricky idea, right? Which is really it's decomposing the rewrite a little bit. And what you'd like to do is to have this be more carefully connected to the rewrite. Right, so you'd like to be able to generate this, from the rewrite rules, generate. So remember here, from the fact that our collection was a set, we used the set operations in our semantics, and we generated these formulae. From the term constructors, we generated the spatial formula. Can we do the same for the modal formula? That's the basic idea. So in order to get to that, we need to go back to the idea of context. So does everyone remember what a context is?
Term with a hole poked in it.
That's exactly right. That's exactly right. So there are contexts that when you put the term in it, we get a red X. What's an example of such a context in the case of the row calculus? So it's a term with a hole poked in it, and when you put a term in, you get a red X. So a red X is a reduction, a term that you can reduce.
So send on X, or receive on X, with some continuation and process being the holes.
Okay, so you put two holes.
Right.
Right. If you only want a one-hole one, so you could put the hole in the where you're sending a Q and leave the continuation filled in, or you could flip it around. You could put the hole where the continuation is, and that would give you a one-hole context. That's exactly right. So you've heard me mention this before, but it bears mentioning again. So Peter Sewell and Jamie Leifer and Robin Milner all observed that if that there's a natural way to use contexts like that one to label transitions. And then you can pick out the minimal contexts that give you rewrites. And when you pick out those minimal ones, and if you pick those as your observations for bisimulation, then you get a bisimulation that's a congruence with respect to the rewrite system. Okay, so that turns out to be a lovely idea. What no one ever noticed, to the best of my knowledge. I mean, I have seen no papers on this, and if you want to do a literature search, you can. Is that you should, once you've made this observation, you should go back and fix the Hennessy-Milner logics. Since we now have a thing that labels the rewrites, we should put that thing inside the brackets of the diamond. In other words, between the two brackets, instead of putting an alpha, we should put a context, because the contexts are the most natural thing to label your rewrites. That's a key observation. And once you do that, then you get this ability to you get this ability to generate the modal formula as well. Now it turns out that we can go much farther. Now I'm gonna conclude the class early today because I need to take care of something before the casters stand up. But what I want to say as a teaser for next time is that if this really does give us a good typing, then we ought to be able to do the same thing for the lambda calculus. We ought to be able to generate a logic in this way for the lambda calculus. And now notice that there is the simply typed lambda calculus where we have types as and in particular we have the arrow type. And the question is, how does the arrow type relate to the types that we generate in this way? And I'll give you a hint. It arises as a result of this context labeled possibility operator. So what I'd like to do is to leave you with an exercise where you take this basic, so you already know the grammar for the lambda calculus, and I'd like you to take a set as your collection and build up the logic for the lambda calculus. So find the logical formulae that show up as a result of running the ladle algorithm on the lambda calculus together with set. And when you do that, then we'll be able to go back. So you only have to give up to the structural stuff. You don't have to give the modal operators, but if you want to do that, that's extra credit. And once you do that, the next week, what we will do is to flesh out the modal operators and find the arrow type as a result of the modal operator. So, in other words, ladle has a result, and has many results. But one of the results is that we are able to give a single uniform interpretation of program behavior that unifies the arrow type with the modal types. So, like, everyone who's done any programming here should know what the arrow types look like, right? Like in Scala or Haskell, we know exactly what arrow types are, right? It's functions that go from the left to the right. So we're gonna unify the arrow type with the modal type. But we'll do that after you guys have had a chance to wrestle with giving a logic for the lambda calculus. And once you've calculated a logic for the lambda calculus, we'll start to see some things that you could do with it. One of the things that's really important, and this is the last thing I'll say before I jump off. One of the things that's really important is that think about how much code there is on the internet. Think about like GitHub. GitHub is a giant database in the sky full of code. And that's just one repository of code. If you look at all the repositories behind the enterprise firewall, then is probably at least as much code out, behind the enterprise firewall as there is out in the public domain and open source repositories. And yet, we can't really search for the code on the basis of how it's shaped or what it does. Now think about the blockchain. If the blockchain is successful, then all the smart contracts we ever write end up being up on the blockchain. So the blockchain becomes an even bigger GitHub than GitHub. And so the next question is, how do you search for smart contracts in a way that's meaningful? Like right now, the way you search GitHub is socially. I know someone who knows someone who knows someone about a repo that has a repo that does what you're looking for. But that's not really very effective. What we want to be able to do is to search on the basis of structure and function of programs. These logics give you the ability to search on the basis of structure and function. And so when you calculate the logic for the lambda calculus, one of the things you might look at is formulae that constrain lambda terms so that you could search for them. And by the way, people have already built this. There's a service called Hoogle, Hoogle, which uses Haskell types to search Cabal. Cabal is the package library for Haskell. Unfortunately, the Haskell types are not interesting. For example, not interesting enough to constrain the searches in a way. So consider the following. Sort takes a list of integers and produces a list of integers. Shuffle also takes a list of integers and produces a list of integers. So, so searching on the basis of Haskell types would not distinguish between sort and shuffle, which is not very good. But when you use the ladle types, it gives you a much better sort of X-ray vision into the structure and function of the terms. So ladle gives us a search language for this giant repository of smart contracts. And that's just the beginning of what ladle does. Okay, so with that, I'm going to end the lecture early. You guys have your homework, and I'm looking forward to see what you come up with.
Thank you.
Thanks,
you.
Greg.
Thanks very much.
Thank you. Ciao, ciao.
Thank you.
Thank you. Ciao.